We're going to go through our momentum and impulse unit test now. You were given your tests back a few minutes ago, and with those tests, you were given a booklet that identified which questions you got wrong on the test. As I go through this test, I want you to make the corrections to your test. You do that, you get a 3% bonus on your test. Now, there's two versions of this test that we're going off of. Same questions, but different order of these questions. I'm going to go off of version A as I give you the solutions to this. If you don't know which version you have, I want you to take a look at question number 1. If that number 1 is italicized, then you have version B. If it's not italicized, then you have version A. So if it's like this one, then you're going to be on the same version of test that I'm going off of. If you have an italicized number 1, then you're going to be going off of the other version. When I'm going through this version A, I'll refer to version B, tell you which question that I'm working on in version B. You're just going to have to flip around a little bit as we're going through this. Okay, we're starting with question number 1. 1, 2, and 3 were the same for both versions. So let's take a look at page 1 for both versions here right now. Which of the following statements best describes an isolated system? We're tempted to put C for this one. Momentum is always conserved in an isolated system. It is. But the best way to describe an isolated system is the definition of an isolated system. We said an isolated system is a system where we have no external forces acting, so A is going to be our answer for that one. Number 2, a batter hits a fly ball. The .130 kilogram baseball moves at a rate of 20 meters per second at the point where it's 5 meters above the ground. What is the magnitude of the momentum of the baseball the instant before it strikes the ground? Now, when we talked about these questions, when we did them early on in February, we called these momentum after acceleration questions. We said there was a couple fairly common mistakes that people would make. One of the common mistakes was forgetting to square the initial speed. Another one was forgetting to even include the initial speed to begin with. And a third one was, and this is the most common mistake that was made on this one, was just using the initial speed and not finding the final speed. We want to find a momentum. We know we're going to say m times v, but we can't just blindly multiply a mass that we're given times any random velocity. That's the wrong answer. This is the momentum of the object, not when it strikes the ground, but when it's 5 meters above the ground. You get 2.6 for that, and 42% of you bubbled in 2.6 for that. But that's the momentum, the initial momentum, before it strikes the ground, or when it's 5 meters above the ground. We don't want that number. We want the velocity as it strikes the ground or just before it reaches the ground. So we're going to have to find that final speed, or that final velocity, using vf squared is equal to vi squared plus 2av. So what do we got here? Vf is the square root of, again, don't forget to include the initial speed here. Most of you did not forget to include that. Don't forget to square it. Most of you did not forget to square it. 20 squared plus 2 times negative 9.81 times the displacement here would be negative 5.00 meters. I'm going to bracket that. And I'm going to put a second set of brackets in here as well. When I sub this into my calculator, I want to double bracket that. When I solve for VF there, I'm going to get a value of 22.3182 meters per second. Now, I don't know which direction that 22 is moving in. Doesn't matter, because we're only looking for the magnitude of the momentum here. So whether it's at an angle, whether it's straight down, doesn't make any difference. The magnitude of the momentum will be the same. Let's take that number. Let's sub that number back into here for the final velocity. Multiply the two together, and we're going to get 2.90 kilograms meters per second. And that should make sense, right? If we had 2.60 kilograms meters per second, the initial momentum, when it was 5 meters above the ground, the only one that it could possibly be would be D. It's got to be more momentum when it starts moving faster as it moves down toward the ground. So D is our answer there. Thankfully, more of you put D than C, but not by much. C was a really common answer. I said, I think 42% of you said C. So watch that. Common mistake. Let's not make that mistake again when it really counts on our diploma exam. 3. Which of the following quantities are scalar quantities? We nailed this one. That's good. We should. This is one of those category 1 questions where we've got to build up our equity so that we can afford to make a mistake somewhere else if we need to. A is our answer, but kinetic energy, potential energy, momentum, and force are both vectors. Any form of energy is a scalar quantity. All right, looking at page 2 here now. Multiple choice number 4, this would be on version B, multiple choice number 7. So I'm off of version A. If you're on version B, this is multiple choice number 7. We see a force versus time graph. We automatically think 3 words when we see the force versus time graph. And those 3 words are area equals impulse. Every single time, area equals impulse. And then, well, we do what we do with every graph that we see. Take a look at our axes and check the units. Are they standard units? Are they non-standard units? In this case, we've got 10 to the minus 1 seconds and kilonewtons. So when we do that area, we're going to have to factor in those 10 to the minus 1 and 10 to the 3 newtons on the y-axis. What are we looking for in this question? It says, number 4, the magnitude of the impulse experienced by the car was blank, and the initial speed of the car was blank. So let's do that here. Let's say the impulse is the area, which is just a triangle. Right? This is the area that we want to find, not all this area right here. Right? That has nothing to do with it. It's just the area between the line and the x-axis. So it's the blue area there. One simple triangle, let's say base times height divided by 2. We're going from 3 to 8 for our base, so that's going to be a base of 5 times 10 to the minus 1 seconds, times the height, which is negative 70 times 10 to the 3 newtons. We'll divide that by 2. We end up getting a value of negative 17,500 newton seconds, or we're going to round that to negative 1.8 times 10 to the 4 newton seconds. So our answer to the first part of the question is, well, it's either going to be A or B, 1.8 times 10 to the 4. The initial speed of the car, you know what else we're allowed to do, right? We always do area equals impulse. We sometimes do delta P is equal to M times delta V. Remember, we never do delta P is equal to F times T when we're dealing with a graph. Delta V is equal to delta P over M. Delta P, we're going to use the unrounded number, negative 17,500 newton seconds, divided by the mass here of 1,200 or 1.2 times 10 to the 3 kilograms. Do the math on that one, it works out to be negative 14.58 meters per second. So if the change in velocity, not the final velocity, not the initial, the change is negative 14.58, and question tells me, I believe, that it starts at rest here. If it, it ends at rest, brings the car to rest. If it ends at rest, if it ends at 0, and the velocity went down by 14.58, then the initial velocity must be 14.58. So we're going to say A is our answer there, 15 meters per second. 1.8 times 10 to the 4 newton seconds, 15 meters per second. A is our answer. Numerical response number 1. We've talked about not this specific question before, but this type of question where we get a bunch of information, most of which is irrelevant. We want to skim through everything, not read it in detail, but skim through everything. And then we want to look at the question and then go back to the information box and figure out what's relevant. So let's pretend that I've skimmed through it here. We'll go to numerical response number 1, which is numerical response number 1, by the way, on both versions of the test. Question says the rifle has a mass of 3.80 kilograms. What's the recoil speed of the rifle expressed in scientific notation? We're analyzing the explosion of the gun/bullet here. The bullet is fired up, the gun recoils down. We don't care about 5 seconds after the bullet is fired. We don't care the altitude that the bullet reaches. We don't care about any of that. We care about immediately before and immediately after this explosion. If we talk about the terminal velocity or the altitude that it reaches, we don't have an isolated system. Gravity has had a chance to do its thing. So we're looking at immediately before and immediately after. Immediately before this bullet is fired from this gun, the velocity and therefore the momentum of the bullet and the gun is 0. Afterwards, we have two objects. We have the gun, that should be M1V1F, and the bullet, two objects, two terms. We're going to say the mass of the gun is 3.80 kilograms. We're looking for VF, V1F, that is the velocity of the gun after the bullet is fired. The bullet is 2 grams. We're going to convert that to kilograms, 0.002 kilograms times 841 meters per second. Now, this one says the initial velocity is 841. We're saying that this is the final velocity. Remember, we had a question in one of our quizzes, or practice quizzes, with the skier leaving the starting gate. We were told that the initial velocity of the skier was a certain value when he left the starting gate. But we talked about that, meaning really that was the initial velocity for the trip down the hill. That was the final velocity for leaving the starting gate. This 841 is the initial velocity for the bullet going up into the air, but it's the final velocity of the explosion. It's exactly like that skier question. We've also said that there's a reason why we get every question. Every single question, there's a purpose behind it. The purpose behind that question that I gave you was just a little lesson in terminology. Just because we see the word initial velocity doesn't mean for us that it is the initial velocity. For us, in this question, it's the final velocity of the bullet. The velocity immediately after the bullet is fired. All right, let's do the math here. We calculate that 0.002 times 841, take it to the other side by subtracting, and then divide by 3.8. We're going to get a value here of V1F. It's going to be 0.443 meters per second. Now, we want to express this in scientific notation, so we're going to make it 4.43 times 10 to the negative 1 meters per second. The value of A, B, C, D would be 4431. 4431. We, when we express this, will not put in the decimal place because they do put in the decimal place. When they include it, we don't. When they don't include it, we do include it. Next question. This is question number 5 for version A, but it's question 4 for version B. 5 for A, 4 for B. In this question, we're looking for the velocity of the 2.4 kilogram piece after the collision. This is a pretty straightforward question. It's a category 2, but we can definitely get this question. This is a collision. We say PI equals PF. There's two objects before, M1 V1 I plus M2 V2I, and we have two objects after, M1 V1F plus M2 V2F. Now, we do have to be careful because we have two objects moving in different directions. Probably should draw attention to that so that we don't forget to include a negative value for one of them. Masses don't cancel because they're not the same. We're going to say 2.4 times 3.2 plus 9.5 times 8.4. But we're going to make that negative because it's to the left. 2.4 times V1F, because we're looking for the velocity of the 2.4 after the collision, plus 9.5 times V2F, which we're told that it continues to move to the left at 5.4, negative 5.4 after the collision. So what you want to do in this one is calculate this value. Calculate this value, take it over to the other side. It becomes a positive on the left side because of the negative right there. And then divide that by 2.4. When we do that, we're going to get a value of V1F of negative 8.7 meters per second, or we're going to say 8.7 meters per second to the left. Next question is number 6, or if you're looking at version B, you're looking at question number 5. An empty freight car of mass M coasts along a track at 2 meters per second. It couples to a stationary freight car of mass 2m. What's the final speed of the two freight cars immediately after the collision? Clearly, conservation of momentum. And we've talked about how we can use impulse for one of these collision questions, but we don't want to do that. Not normally, at least. If we do, because we're looking to solve for a force, then we would have to choose either the empty freight car or the stationary freight car and run with one of them, okay? One object or the other. If we want to analyze the entire collision, then we've got to do conservation of momentum. All right, PI, we're going to say there's two objects. There's the empty freight car plus the stationary freight car. And it says they stick together, they couple, so we're going to say the final momentum is just m total times VF, one object, one term. Now I'm going to cross this off because the second freight car is at rest. The first freight car has a mass of m, whatever that is. The total mass would be 3m, m plus 2m is 3m times VF. We're solving for VF. Now, some of you guys may have subbed a number of 1 in for mass, but in the end it doesn't matter because mass cancels. It's in both terms. We get 2 is equal to 3 times VF. VF is going to work out to be 2 divided by 3 is 0.667 meters per second. So the answer for this one would be D. Next question for version A is numeric response number 2. If you're on version B, you would be looking at numeric response number 3. Numeric response 2/3. We've got this scenario where we've got a movie stunt with a truck and a train locomotive intentionally crashing, and the diagram is illustrated below. It's nice when they give us the diagram because we got to draw a diagram anyways so that we can show our givens and visualize it. They've done it for me here. We want to find the magnitude of the momentum immediately before this collision takes place. Immediately before this collision takes place. And that includes magnitude and direction. Now, there's two ways that you can tackle this. You can find the final momentum of this system and then say, once you find the final momentum, well, it's the same as the initial momentum, right? Because PI equals PF. You would find the final momentum by going X component, PI equals PF, Y component, PI equals PF. Find the final momentum, X component, find the final momentum, Y component, and then you're going to combine them. And you solve for PF and the angle. Now, some of you probably did that, and that's good, that works. There's another way to do this as well. By the way, that's solving for the final momentum, but we know that's going to be equal to the initial momentum. The other way to do this is just to solve for the initial momentum right off the top. The momentum of this one, 3 times 10 to the 3 times 33.3 is 99,900. and that's upwards, right, to the north. The momentum of this one is 4.5 times 10 to the 4 times 10, which is 4.5 times 10 to the 5 kilograms meters per second. Now, some of you, when you were finding the total momentum, just said, well, 4.5 times 10 to the 5 plus 99900 is 5.5 times 10 to the 5. Well, that's adding scalars. We can't do that. We have to add them as vectors. So let's do that. The x component of this is 4.5 times 10 to the 5. This is the initial momentum. The x component of the initial momentum of the truck is 999, this is the y component, sorry, kilograms meters per second. We're going to calculate this value of p. We end up with the same triangle as we ended up with for the final momentum using the other method. This is a little bit more of a direct method, though. We do this Pythagorean theorem. We're going to end up with a value of 4.6 times 10 to the 5 kilograms meters per second, not 5.5. If you add them as scalars, you get 5.5. If you add them as vectors, you get 4.6. We can calculate this angle as well using the tan function. That's going to give us 13 degrees north of west. So 4.6 times 10 to the 5 for the magnitude, 13 degrees north of west for the direction. Now, they want me to express this, the magnitude of the momentum, 4.6 times 10 to the, it was 10 to the 5, but it doesn't really matter because we just want A and B. Don't put the decimal place there because they do. Now we also want the directions, the direction in degrees, north of west. We just found it, north of west. If you drew your vector diagram the other way, you would have gotten 77 degrees west of north. That's not what they ask. They ask it north of west. So it's 4.6 times 10 to the 5 kilograms meters per second at 13 degrees north of west. So 4613 would be our answer for this one. Question 7, this is question number 6 on version B. So question 7 on version A, question 6 on version B. You get this pool table where the cue ball is striking another ball, the 8 ball. The 8 ball deflects up at 40 degrees, and we're looking for the speed of the cue ball after the collision. It says the maximum speed because, as we know, like immediately after the collision, it's moving its max speed, but half a second later, it's probably going to slow down a little bit, right? We want to look for the speed immediately after the collision so that we have an isolated system. In other words, we want to find that maximum speed. We have, you can see it there, we have a funny angle, 40 degrees. And what do we say when we see a funny angle? I don't like funny angles. So we take it off to the side and we get rid of it. Now, some of you probably found the x component and the y component of the momentum. That's okay. I did it with velocity. Either one is okay. I'm going to find x and y of the velocity. You chose momentum, that's fine. The x component here is the adjacent side, so we'll use cosine 40 degrees adjacent over hypotenuse. The adjacent side is 2.4513 meters per second, and the y component, sine 40 degrees, is equal to y over, opposite over 3.2. The y component ends up being 2.056 meters per second. Well, now we got to do our x and y components. Actually, let's first replace that. I like to scratch this out. I don't really care about any of that now because that 3.2 meters per second is dead to me. We have an x component and a y component. That was the whole point of taking it off to the side, was to replace that 3.2 meters per second. Okay, now we can do the x and the y components. We're going to say M1 V1I, which is just 0.72, right? They've already done that math for me. 4 times, or 0.18 times 4 is 0.72, plus 0, because the 8 ball was initially at rest, equals, I'm going to say the mass of object number 1, the cue ball, 0.180 times V1F plus 0.160 times, not 3.2. 3.2 is dead to me. Rather, I'm going to use the x component of that final velocity, which is 2.4513. So let's take this number over to the other side, divide by 0.180. We should get a value there, V1F, of 1.8211 meters per second. We'll do the same thing for the y component. This time, everything is 0 before the collision. You get that cue ball, but it's moving on the x-axis, so it doesn't count for the y-axis. 0.180 times V1F plus 0.160, it's the mass of the second object, the 8 ball, times the y component that we already found, 2.056. Let's calculate V1F here, and it works out to be negative 1.8276. So what do we got here? We have 1.8211 to the right, and we know that the other one is downwards because it's a negative value for the y component, 1.8276. And the hypotenuse there, what I'm looking for, we could find the angle, but we're not asked to solve for that. We just do the Pythagorean theorem to find the hypotenuse there, and it's going to work out to be 2.58 meters per second. You guys did overall a decent job on that one. About 2/3 of you got that one right. That's a category 2, a little harder category 2 than that other one though. We can get this, but it's a little bit more challenging than some of them. Question 8. Doesn't matter which test you were on. This was question 8. Love this question. I warned you this was coming. Didn't tell you exactly what it was going to look like. But coal chute angled at 30 degrees to the horizontal releases 15,000 kilograms of coal to fill a stationary, empty 5,000 kilogram cart. The cart and the coal move forward with a horizontal velocity of 2.0 meters per second. This is one of those problems where the Earth becomes part of the system. This coal cart and coal afterwards, they want to go down like this somewhere, but because they have to push the Earth down to go down that way, and the Earth is so bloody heavy, the y component of the final velocity effectively ends up being 0. And almost all of you recognize that. Almost all of you spotted that. Almost all of you did the x component, whether you labeled it x or not, you effectively did the x component. M1 V1I, this would be the coal, plus 0, because the cart was not moving before the collision took place, equals mass total times VF. M1, that would be the coal, 15,000 kilograms, times V1I is 20,000 kilograms times VF of 2.0 meters per second. And when we calculate that, we're going to get 2.7 meters per second, and we bubble in the velocity, the speed of the coal along the chute is not 2.7 meters per second. What have we just found? What have we just found? That 2.7 meters per second. Half of you, by the way, recognize what this is. Half of you recognize that v1i 2.7 is the x component of the velocity of that coal before it hit the cart. The other half of you didn't recognize that and circled B. The half of you that did recognize it said, wait a second, I'm looking for the speed of the coal along the chute, so I've got to find the hypotenuse here. We're just going to say cosine 30 degrees is equal to adjacent 2.7 meters per second over the hypotenuse, which is really what I'm looking for here, the speed along the chute. V is equal to 2.7 over cosine 30. It was almost exactly evenly split between B and C, but C is our answer. C, people that put C are the people that read the question and answered the question, recognized what we were asked to find, the speed along the chute, not the x component of that speed. Big page of information here. We know what to do, right? We skim it. Don't pay too much attention to things. We just kind of skim it, get the gist of it. And then we flip the page. And then we look at the question. Or the questions in this case. There's 4 of them that go along with this. What am I asked to solve for? The magnitude of the momentum of the landing unit as it entered the Martian atmosphere. The magnitude of the momentum as it entered the Martian atmosphere. Okay, to find the momentum at any given time, it's just m times v. We multiply these two numbers together, 3.6 times 6.0, and we get our answer, 2.16 times 10 to the 5 kilograms meters per second. That's a pretty straightforward question. 10, the airbags protected the landing unit by. We don't even really need to go back to the information for this. What do airbags do? They cushion an impact, right? What's the physics of cushioning an impact? The impulse is the same. The impulse is the same no matter how something lands. But if we cushion it, the time goes up. So the force would go down. The answer to question 10/11. By the way, this is number 9 was 11 for version 2, version B. Number 10 is 12 for version B. The answer to question 10/12 is C. It increases the time of contact with the surface by the landing unit. 11/13 for version B. The magnitude of the impulse, the change in momentum experienced by the landing unit during its first collision with the surface of Mars is what? The magnitude of the impulse during the first collision. We're going to say for this one, this shouldn't be that hard, but you guys did not do great on this one. M times delta V, we've got a mass here of 360 kilograms, and delta V here, this is where you guys messed up. Delta V is VF minus VI. The final velocity just after it rebounded is 11. The initial velocity just before it hit was negative 18. So we're going to say final velocity versus minus initial velocity. 11 subtract negative 18, not positive 18. Lots of you forgot to include, about a third of you forgot to include that negative. Momentum's a vector. Even though we're only looking for the magnitude of the momentum, we still have to include the direction of the velocity in our equation. When we get a final answer, we just don't care what the sign of that final answer is, that's all. We do the math on this one, it works out to be 1.0 times 10 to the 4 Newton seconds. So the answer for this one is going to be D. The most common incorrect answer was C, and that was because you forgot to include the negative of the initial velocity. 12, the collision of a landing unit with the surface of Mars. This is 12/14, sorry. The collision of landing unit with the surface of Mars is classified as, and what kind of collision is it, elastic or inelastic? Well, there's only one thing moving here, and it's the landing unit. It was moving at 18 before it struck. Now it's moving at 11 after it struck. That means that kinetic energy is lost, right? You can calculate the kinetic energy if you want, but in the end, you know that 11 meters per second is going to give you a smaller kinetic energy than 18 meters per second. So it's got to be inelastic because kinetic energy is not conserved. Momentum is always conserved, right? So we know that that's not the answer. 14 is D. Sorry, 12/14 is D. Numeric response number 3, or for those of you who have version A, version B, sorry, it would be numeric response number 2. Numeric response 3/2. Some of you put way more effort into this one than you had to. 1,000-kilogram car traveling at 29.4 hits a parked truck. Immediately after the collision, the car was moving at 20 meters per second, 20 degrees north of east, and the car was moving at an unknown speed, 45 degrees south of east. What's the total momentum before the collision? Don't make this harder than it has to be. The total momentum before the collision is the same as the total momentum after the collision. But boy, oh boy, it's way easier to find the momentum before the collision. There's one object that's moving. The 1,500 kilogram is parked. So the total momentum before the collision is just the mass of the 1,000-kilogram car times the velocity of the 1,000-kilogram car. We do the math there, it works out to be 2.94 times 10 to the 4 kilograms meters per second. We're going to express that A, B, C, D. A, B, C, D. We do not include the decimal place because they do include the decimal place. Some of you went and did components of this and found the final velocity of the second object and then used that to find the final momentum of the system and said that's the same as the initial momentum, and that's correct if you do it all correct. But boy, with the amount of work that you'd have to do with that, the chances of making a mistake in the math there are pretty high. Way easier just to find the initial momentum. Don't overlook the obvious. If you're given a gift, take it. Multiple choice 13/9 for version A. Two carts traveling at the same initial speed move toward each other on a table as shown below. Cart 1, 500 grams, cart 2, 250 grams. They collide. After contact, they remain separate from one another, move off independently. Which of the following vector diagrams drawn to scale shows the magnitude and the direction of the impulse experienced by each car? Most of you recognized, to your credit, that the impulse must be equal and opposite. So most of you said either A or D. That's good. But about 20% of you incorrectly chose D. The answer is A here. Now, why is it A? Let's pick one object here, okay? Let's say cart 1 is moving in the forward direction. It loses momentum in the forward direction. As it's moving to the right, it loses momentum. That's a negative impulse. Cart number 2 is moving in the negative direction. It's moving to the left in the negative direction. It loses momentum in the negative direction. When we know this from the first day we learned about impulse. When we lose momentum in the negative direction, that's a positive impulse. So the answer for that one is A. During this collision, momentum is 100% conserved, and kinetic energy is most likely, we know that 90% or more of collisions are inelastic, which means that most likely kinetic energy is not conserved. By the way, this is multiple choice number 10 for version B, people. Number 4, golf ball has a mass of 45 grams. You've got to convert that to kilograms. Club is in contact with the golf ball for 3 times 10 to the negative 4. Here's the final speed. We want to find the force. We're just going to go F times T equals M times delta V. So we're going to say, what is this? 0.045 kilograms times VF minus VI. We're going to say 72 meters per second minus the initial velocity of 0 over the time of 3 times 10 to the negative 4. We do the math for that one, and we get 1.08 times 10 to the 4 newtons. We're going to express that as 1.08. This time, we do include the decimal place because they don't include the decimal place. When they do, we don't. When they don't, we do. That was numeric response 4/4 for version A and B. Number 15 is 15 for both versions, version A and B. Tennis ball with a mass of 110 grams, 18.5 to the east, struck with a force to the west. Let's draw attention to that, the fact that we have 2 different directions there. Ball and racket are in contact for 3.20 milliseconds. What's the change in momentum here? I can use F times T or M times delta V, but it looks like my givens fit this one the best. 950 times 3.2 times 10 to the negative 3. If you used the 18.5 here, the fatal flaw here was that you multiplied M times V. We want to multiply M times delta V, and we don't know what the final velocity is. We only know what the initial velocity is, so we can't do this. We don't have the change in velocity. But we do have the force and we do have the time. We multiply those 2 together, we're going to get 3.04 times 10 to 3.04 kilograms meters per second. Technically, it would be negative, I guess, because my force is to the west. 3.04 to the west. Most of you that got the wrong answer just said M times V. Remember we said early on when we did impulse, we want to write down the equation M times delta V so that we don't forget to include a final velocity. We don't have a final velocity here, so we can't include it. It means we can't use that equation. 16/16. Which of the following units are correct for momentum? That would be C, Newton seconds. And the last 2 questions, 17 and numeric response number 5 for both versions of the test. Glass ornament sitting on a table. It breaks into 3 pieces. Fragment A is 168 grams. Fragment B is 212 grams. And fragment C is, we're not told. We can figure that out, though. We know that the total mass is 575. If we subtract 168 and 212 from 575, we're going to get a value for the third piece of 0.195 kilograms. We're looking for the momentum of that third piece there. Okay, I see a funny angle. 60 degrees, 120 degrees. Doesn't matter which one you use there, 60 or 120. I use the 60 to be honest, but in the end, if you go cosine 60, cosine 120, sine 60, sine 120, the only difference is the sine that you get. I'm going to use the 60 because it makes a little bit more sense to me. 60 degrees. I'm going to go with momentum on this one, I think. The momentum of this is 1.91. Let's find the x component of the momentum and the y component of the momentum. We're going to use cosine for the x component. sign for the y component. When I do that, I get an x component of 0.955 kilograms meters per second, and the y component, using the sine function, is going to be 1.6541 kilograms meters per second. So let's replace this 1.91 with these two components that I just found. Scratch those out, because those values are dead to me now. Okay, now let's do our thing. X and Y components. Zero initial momentum because they're sitting there. If we're doing momentum, then the first object has a momentum of 2.52. We could say m times v, but if we multiply m and v, we just get 2.52 anyway. So I'm just going to accept the gift and use the value of the momentum that's given to me. It's all x component. The x component of object number 2, however, is negative 0.955, negative because it's to the left. And the x component of the third piece, well, we're going to solve for that. When we do, we get negative 1.565 kilograms meters per second. And the y component, 0 initial momentum equals 0 final momentum for object 1, because it's on the x-axis, plus the y component of that is 1.6541, positive because it's up. Solve for P3 for the y component here. It's going to work out to be negative 1.6541 kilograms meters per second. Now we're just going to redraw this. 1.565, 1.6541. And let's solve for the magnitude of that momentum. Remember, we were finding momentum here, dealing with momentum as opposed to dealing with velocity. You could have done it with velocity. I just chose to deal with momentum because that's what I'm solving for in this question. Do the Pythagorean theorem. When you do, it works out to be 2.28 kilograms meters per second. So the answer to that question would be C. And finally, question 5, the speed of the third fragment. All we're going to do for this one is say P is equal to m times v. V is equal to P over m. I'm going to go 2.28 divided by the mass of 0.195 kilograms. It's going to give me a value of 11.7 meters per second. Or they tell me to express this in scientific notation to 3 digits. So that would be 1.17 times 10 to the 1, or 1.17. They don't include the decimal place, so I do include the decimal place. 1.17 to 3 digits. Now, some of you got number 5 marked correct and get a different answer. If you said A for question 17, you had no hope of getting number 5 right. But I marked it right, as long as your answer for number 5 was consistent with your answer for number 17. So you could have got 1.17 is the correct answer, but if you said 2.66 for the speed, that was the speed that was consistent with saying A for number 17. I would have marked that correct. If you said 1.97, then that was consistent with B. 1.17 obviously was correct because that was the correct answer. It's consistent with C. And if you said 3.13, This should actually be 2.66 times 10 to the 1, 1.97 times 10 to the 1. This one should be 3.13 meters per second. Again, wrong answer, but it's consistent with you choosing D for number 17, so I would have marked that correct. If you missed something with the corrections here, you can always pop in tomorrow. I can help you out with something. If you didn't miss anything, super. We'll take a look at it, give you a 3% bonus marks. I'm going to ask you now to put your little booklet where you've done your corrections around the test question booklet. So your test question booklet should be inside that correction sheet. And I'm going to ask you to hand them back in to Mr. Better.